think we can start, and if people join a little bit later,
that's fine.
That's their problem.
Okay, yeah. So then, as I say, just let me know. Let's say at about 30 minutes or so.
Perfect.
I have an idea of how much I should speed up or not.
Perfect.
So the talk is on optimal quantum channels, and I show here the published version of the paper, the title page, just if you're interested to look at it. And I'll be discussing the paper, but I'll focus more on some of the conceptual background that I don't discuss in much detail in the paper. And on the other hand, the technical details in the paper, I won't discuss in any detail. So it's more a complement or an introduction to the paper. And I'll start off with just a global overview of what it is that I'm doing in the paper. And once I've done that, I'll come back and I'll fill in some details and fill in some background and motivation. So the basic problem is to consider two systems, A and B, and I'll focus on finite systems with finite dimensional Hilbert spaces. And I look at density matrices of each, so rho 1 up to rho L of system A, and similarly for system B. And the aim is to find a channel from A to B that satisfies this restriction. So you want to map the first state to the first of the second system, etc. But we want to minimize a certain observable of the composite system, AB, which I'll call the cost matrix. And the cost of the channel will be expressed in this way. So it's the trace of C times this kappa E, where kappa E is given by the Choi-Jamalkovsky duality. So it's a state of the system AB given by the channel E. And as I say, I'll motivate this in a bit more detail later on. So in other words, in very short terms, I want to find channels satisfying this while minimizing the cost. So just to say it again, you start off with states of each of the two systems. You want to find channels that map A states to the chosen states of A to the chosen states of B. So it's certain tasks that you want to perform. And you want to find a channel that minimizes a cost given in this form. So that's the basic problem. And I'm going to discuss the classical case of optimal transport, which was the main motivation for doing this. And then I'll return to the quantum case. And you're welcome to, if there's a question along the way, you can tell me. So classical optimal transport, I'm going to describe in very simple terms. I'm going to think in terms of warehouses and shops, which are spread around some country. And the idea is to try and find the cheapest way to transport the goods from the warehouses to the shops, right? So if I look at this picture, you have warehouses here on the left, you have shops indicated on the right, and let's view a truckload of goods going from the warehouse to the shop. So if I label the warehouse X and I label a particular shop Y, then I can think of this truck going from X to Y, and I can label this transition, this truckload, by XY. And similarly, one can do it between any warehouse and any shop, and even multiple trucks can go from the same warehouse to the same shop. And I'll view that such a truckload as in a sense, a basic unit or a minimum unit in terms of which we'll work. So I'll call that a elementary transition. Now, this elementary transition, this terminology is not actually standard in classical optimal transport, but it's a useful concept in terms of which to think of when we move to the quantum case. But that's the basic picture. You think in terms of basic units of goods, in this case, going from some warehouse to some shop. So that's the simplest way to explain what is happening. So I think of the set of warehouses as set X, the set of shops I call Y. And if you think of this XY, you can view it as this elementary transition. So recall I set a truckload going from X to Y. I will label xy, and I call it a elementary transition, you can think of that as a pure state of the compound system xy. In the classical terms, that's exactly a pure state. If you were to think of a state of one classical system and a second state of a second classical system, pure state in each. So in other words, think of a point in a phase space, then the combination of the 2 points would be a pure state of the compound system. So in other words, we identify transition from x to y with a state from x to y. And just to remind you, if we think in terms of this duality, it's a duality between channels and states. The channel, in a sense, is dynamics, and you would describe it in terms of a state or vice versa. And you see that the same idea is present here. A transition from x to y is identified with a state from x to y. In this case, we're looking specifically at a pure state. So this is roughly what's done in a classical case, though they typically express it in terms of a distribution over x and a distribution over y. Just one distribution over x, one distribution over y, and they think in terms of the total transport from x to y. Here, for simplicity and in terms of comparison with the quantum case, I'm in a sense decomposing it into these elementary transitions. Now, there's some cost involved. I mean, it takes some amount of money for a truck to go from x to y, and we'll assume the cost depends only on x and y. So it's fixed. If you specify x and y, there's some fixed route and some fixed amount of fuel, etc., that's used. So we attach a cost to each such elementary transition. And secondly, we denote by omega xy the number of times the elementary transition xy is used during the transportation of goods. So if you look at this picture here, ultimately I would like to take all the goods spread over all of these warehouses. I want to take it to these shops, and I want to take it to specified distributions. This shop may need a certain amount of goods, this shop may need a different amount of goods, etc. So I want to take all of the goods here, some distribution of goods in other words, and I want to transport it to some specified distribution on this side. And the way to do it is to specify how many truckloads have to go from X to Y for every pair XY. And this is called the transport plan. So in other words, you may have 2 trucks going from this warehouse to that one truck going from this one to that one, from this one to that one, etc. So if you specify how many trucks goes from this warehouse to that shop, if you give it for all, if you give that number for all the elementary transitions, then we call it a transport plan. So the total cost of the transport is then the cost of a particular elementary transition times the number of times that elementary transition is used. And you sum all of that up. That's the total cost of transport. And this is in a classical case, this is what they want to minimize. You do the sum over the costs over all elementary transitions, and you ask which transport plan makes this a minimum. And again, just to remind you, we specify distribution here. So the goods are distributed in some way here. There's some specified distribution that we need to attain here. And this is then a total cost involved, and we need to get a transport plan omega that minimizes that cost. So that's in very simple terms what happens in a classical case. So for example, if you look at this, we have 2 truckloads going from this one labeled X to this warehouse labeled X to shop labeled Y. Since it's 2 truckloads, I have to multiply the cost of a single elementary transition by 2, and similarly for all the other ones. And you add it all up, which is exactly this total cost of transport. So the idea is fairly simple. In fact, it's a very old problem, but even in a classical case, mathematically, it ends up being surprisingly difficult to build a theory around this. And it's only in the past few decades, it seems, that people have been able to do this very successfully. And typically in the mathematical literature, what they do is they normalize the distributions to probability distributions. So you have some initial distribution of goods, let me call it rho X, over the warehouses, some distribution that I'm aiming for. So this is what I start off with. This is the target distribution of goods over the shops. And then the transport plan omega, and again, omega, just to remind you, it's the number of times each elementary transition is used. So it's the number of trucks in each case. Then that transport plan omega itself becomes a probability distribution over the compound system, xy, and it reduces, if you reduce this probability distribution to x and y respectively, then you get those distributions, rho X and rho Y respectively, simply because all the goods from the shop, from the warehouses are transported to the shops. So one can check that fairly easily, that the transport plan is in fact a coupling. It reduces to the two separate, it's itself a probability distribution, reducing to those two probability distributions that we give for the warehouses and the shops. Now, Villani's book, Topics in Optimal Transport. So Villani, by the way, is a fields medalist. He did quite a bit of work in optimal transport and related matters. And in one of his books, Topics in Optimal Transport, he gives a simple diagram, which I adapted slightly, but it gives a good idea of what's happening. You have a probability distribution over X. You have a probability distribution over Y. Here it's over X, it's indicated as positive, so the warehouses are filled with goods. Here it's indicated as negative, so the shops are empty. And then you have this, what I call an elementary transition. You can take a little bit from X to Y, and once you've moved all the goods to all the shops, you've completed the transport. And again, just as I've explained earlier, there's some cost involved that you want to minimize. So that's the basics of the classical case. If I summarize it in simple terms, just to make the main point clear, you have a probability distribution over the warehouses. This is what you start off with. You have a probability distribution over the shops, which you aim for. You have a transport plan, omega, over the compound system, xy, which reduces to rho X and rho Y respectively. So schematically, I can show it like this, that you have distribution rho X here, distribution rho Y here, and this distribution in between is the transport plan. It's, in a sense, the dynamics that takes goods from X to Y, and we want to minimize the cost. So that, in very brief outline, is what happens in the classical case. Now, of course, what I did in the quantum case earlier is I had multiple distributions that I start off with and multiple distributions that I end up with. So I'll still have to generalize a little bit I still have to generalize the classical case a little bit to correspond to what I described earlier. But you can think of this as the classical case of what I had here at the beginning. But just for one initial state and one final state. So the classical optimal transport typically begins with one state, it ends with one state. I'm generalizing in the same process, but otherwise the idea is essentially the same. And again, just to emphasize it, the transport from X to Y is expressed as a probability distribution over the composite system. In other words, the state of a composite system or a compound system is the transport plan, or the dynamics in a sense. So let's return to the quantum case. So I'll look at a mixed state of some quantum system A. Similarly, a state of system B and their density matrices, of course. And via some transport plan, I want to attain exactly the goal that I mentioned earlier. I want to take state rho A to state rho B using a transport plan, and the transport plan itself is a state of the composite system. So it's exactly this idea: initial state, final state, and the state of the compound system acts as the transport plan. So it's exactly that same idea, just the quantum case. State of system A, state of system B, state of the compound system, which again, as I said, reduces to rho A and rho B respectively. So it reduces to the two system states respectively. And that state is what describes transport from system A to system B. Now, the classical cost was expressed like this. An exact analogy to this, in the quantum case, we'll express the cost in this way. We'll have some cost matrix, an observable of the compound system or the composite system, exactly like we had the classical cost. It's a function of pure states in a composite system, xy. Now, so it's an observable on that composite system, classical observable. You simply have a quantum observable on the composite system, and you sum it up over multiples, the number of times you make use of a specific elementary transition. In other words, you have a transport plan, and that transport plan, recall, is a distribution which is now replaced by a state. So this is an exact quantum version or quantum analog of the classical transport cost. Right, so again, rho AB is now simply in the place of what I previously called omega. And for that reason, even in a quantum case, I'll call this rho AB, which reduces to rho A and rho B respectively. I'll call it a transport plan, right? So these couplings are referred to as transport plans. By coupling, I literally just mean exactly this. It's a state on a composite system reducing to the two separate states. That's what I mean by the word coupling. So we are, even in a quantum case, we're after transport plans, in other words, states of the composite system, minimizing the cost while giving, while taking the initial state to the final state. Right. So that's exactly a quantum analog of the classical case. And ultimately, I want to express this in terms of quantum channels. So I don't want to express it simply in terms of a transport plan, but in terms of a quantum channel, using the duality between states and channels. So in outline, I'm going to say it again. You have an initial state, a final state, a channel, which you want to find, which takes the initial to the final state. We associate it. We associate this channel with a transport plan. We'll label it by kappa sub E, and we assign a cost in this way. So all of this is pretty much exactly what we have in a classical case, just translated to the quantum setup. By the way, so as I've mentioned, all of this I'm currently looking at in finite dimensions, but much of this works much more generally. So the association or duality between channels and states can be done in a much more general context. I'm looking at the Choi-Jamalkovsky duality specifically. It's well known and fairly simple, and is well suited to what I'm doing at the moment. But the duality does work much more generally, so it's important to keep that in mind. So in other words, there's much room for generalization at the moment. Well, let's come back to the problem I mentioned at the very beginning. I actually want multiple states, multiple initial states, so states of A. I have some target states of the system B, and I want this channel to perform all of these tasks. So in other words, to take row 1 of A to row 1 of B, up to row L of A, taken to row L of B. So all of these tasks for J from 1 to L has to be performed. It's just a simple generalization of what we had previously, right? In this case, one state going to that state. It's just generalizing it to the situation I had initially. So we're essentially back to where I started off with in the talk. And we want to minimize the cost of the channel. And again, the cost is expressed as this via the Choi-Jamelkovsky duality. So I have my channel E. It has to satisfy these conditions, but at the same time, it has to minimize this cost. The reason I'm using the Choi-Jamelkovsky duality is in part because the state always reduces to the maximally mixed state of A. So to be more precise, this is a duality between channels from A to B and states of AB reducing to the maximally mixed state of A. So it's a specific case of the duality between states and channels, but it's convenient because this maximally mixed state essentially serves as a reference state, which is what makes it unambiguous that I have multiple initial states. So in the classical case where you have one initial state, if you look carefully at what they do, they actually work with that initial state as a sort of reference state. So choosing the Choi-Jamelkovsky duality does deviate slightly from the classical case in a sense that it in effect introduces the maximally mixed state of A as a reference state. And of course, I am making a choice of basis, right? So I've been assuming, I suppose, that you're fairly familiar with the Choi-Jamelkovsky duality, but just to be clear, these are basis states for the state space of A. So I am making a choice of basis. More precisely, I'm making a choice of a maximally entangled state of the two systems, of the compound system AB, and it's expressed, if you just remove the E here, then the state that you remain with here would be the density matrix representation of that maximally entangled state of A and B. So it's that maximally entangled state of A and B that's really being used as a reference, and then on A you can think of it as a maximally mixed state of A, serving as a reference state on the system A. And again, that makes it ideal for transport of multiple states. Right, so as I mentioned, we're essentially back to the beginning of the talk, so that short overview I gave is hopefully now been given in somewhat more detail. And what I want to look at is just some differences between the classical and the quantum case. Again, I'll do it more conceptually. I won't go into much technical detail. You can look at the published paper for that. But I just want to show you why it is somewhat different, and in some ways very different from the classical case. So this brings us back to the idea of elementary transition. So in the classical case, you'll recall it's just a pair XY, X being a pure state of the warehouses, Y being a pure state of the shop. So in other words, X is some warehouse, Y is some shop. Then that pair XY is viewed as an elementary transition from warehouse X to shop Y. And we can think of elementary transitions in the classical case as well. So if I have a channel E and I look at its state representation via the duality, then I can take that state and I can diagonalize it in terms of pure states. By pure state, I still mean it's a density matrix, but a pure state density matrix. So it's given by some state vector. So you can diagonalize it. It will look like this. It's not a unique, the diagonalization, of course, need not be unique, but you can diagonalize it. And then in such a diagonalization, you view each of these pure states essentially as elementary transitions. So that's in, just taking you back to the classical case. Let me quickly show you again. If you think of the pure state of the system XY as an elementary transition, then you're going to think of pure states in a quantum case as elementary transitions as well. So if I take the state kappa E, which represents the channel E, and I diagonalize it with these kappa alphas being pure states, then I'm going to think of each kappa alpha as a pure state. And by inverting the duality, I can in fact express it as a map. So this formula here essentially just inverts this duality to express the maps in terms of states or vice versa. So you get a set of completely positive maps. They're not channels in general, but you can view them as a way to express the elementary transition either as a pure state of the composite system or as a map from the system A to the system B. So in other words, not quite as a channel, but as a map from the mixed states of A to the mixed states of B. The formula involves a partial trace here, you'll see. And if you study the mathematics behind this carefully, you'll see that because I'm choosing a basis, or more precisely a maximally entangled state, there is a certain ineffective choice of basis, and a transposition relative to that basis then becomes relevant. Now, if you compare the decomposition of the states and you look at the maps representing those pure states, then you can show very easily that the channel is in effect decomposed in this way. So it follows directly from this and this. So the formula for kappa E and this inverted inversion of the duality for the E alphas gives you such a decomposition of a channel into elementary transitions. And this allows us to view the total cost of transport as the expected value of the costs of the individual elementary transitions. So that gives you a fairly clear conceptual meaning for the total cost of transport. It's simply the expected value of the costs of the individual elementary transitions. And this is well, at least I found it useful to think of it in this way, because it in part clarifies the relations to the classical case, but it gives you in principle a simple physical meaning or quantum mechanical meaning for the total cost. It's you decompose the channel into elementary transitions. There's in effect a cost involved for each elementary transition, and the total cost is then an expected value over all of those elementary transition costs. Right. So again, I've mentioned this, but I'm just mentioning it again. You can view an elementary transition as a map or a state, and the state is analogous to the XY, the pure state in the classical case. But to connect it to channels, quantum channels, it's more convenient to think of it as a map. Now, these elementary transitions in the quantum case can be much more interesting than in the classical case. And this is basically due to entanglement. So keep in mind, in the classical case, elementary transition is simply X, Y. You can take one truckload of material or goods from a certain warehouse to a certain shop, and that's it. That's the only elementary transitions that are involved. And in the quantum case, you have an analogy of this. If you think of an elementary transition given by this form, V and V dagger on either side, with V being this operator, then plugging this into the duality, it leads to this vector state. So it's simply a transition from the state K of A to the state L of B, expressed as a map or as a state. And that would correspond to the X, Y in the classical case. But something that does not appear in the classical case at all is if you use a unitary channel. This channel, in fact, is an elementary transition. So in the classical case, the elementary transitions will not be channels, right? So, and this is reflected in the fact that let's say the analogy of the classical elementary transitions are simply these very simple maps. They're not channels in the quantum case. And this is the best that you can do in the classical case. Here represented on the quantum states, but that's the best you can do in a classical case. You only have these very simple elementary transitions. But in the quantum case, a unitary channel, in other words, given by a unitary map, let's say from the system A to itself, is in fact an elementary transition. So the elementary transitions in the quantum case are potentially much more involved than in the classical case. Because as this is a channel, but also an elementary transition, it means a single elementary transition can perform the complete transport, which is very, very different from the classical case where you necessarily need many elementary transitions in order to build up the transport. And because of this, there's potential for entanglement to lower cost. If you can use fewer elementary transitions with low cost, then you can, in principle, attain lower cost in the quantum case as opposed to the classical case, where you necessarily need many elementary transitions, and it's more difficult to avoid expensive elementary transitions. So there you would really need all elementary transitions to be very cheap. Whereas in the quantum case, if you can just find a small number of low-cost elementary transitions, that may in fact still be sufficient to perform the complete transport. And I'll express it schematically like this. This is a similar picture that I gave, or the same picture that I gave earlier on. You need multiple elementary transitions in the classical case to perform the complete transport. You cannot just use one elementary transition and be finished. To move all the goods from all the warehouses to all the shops, you need multiple elementary transitions, some of which could in principle be very expensive and therefore raise the total cost. But in the quantum case, it is in principle possible to have a single elementary transition that performs the complete transport. And if that single elementary transition is cheap, then that's it. You have very cheap transport. This is an extreme case of a single elementary transition. More likely you will need a few of them, but in principle you could have a few of low cost performing the whole transport, as opposed to the classical case where you need many and the chances are less likely that all of them will be cheap. So lower cost in the quantum case seems plausible and possible because of the richer set of elementary transitions. And so here I'm essentially just saying what I just said now. If you have a single quantum elementary transition that happens to be cheap, then the complete transport is cheap. In a classical case, this is much more difficult to attain. You cannot expect to just use one elementary transition. You will need to use many. So all of them have to be cheap in order to get cheap transport. And then the final point I'll make is simply that I was trying to think of a possible application of this. And what I wondered about, and this is maybe something where you could tell me if this is a sensible application, but I was wondering if one can use this to construct or find channels that in a sense cause minimal disturbance. So if you have a channel from a system to itself, so some in states and out states, and E is supposed to satisfy these relations, so it should perform all of these tasks. It should take all of the in states to the corresponding out states, which we specify, but we want to otherwise disturb the system A as little as possible, or we want to disturb the state of A as little as possible. Then a possibility would be to set up a cost matrix that looks like this. You look at matrices that generate the second copy of the system A, and let's suppose the system has m by m matrices as its observable algebra, so it has an m-dimensional Hilbert space. Then this is a possibility as cost. This notation, the square here, is just the square of the operator, essentially, or the observable. So the idea would be to find channels performing these tasks while minimizing this cost. And that appears to be a way to frame this problem, disturbing the remaining states of A, so to speak, as little as possible. It appears to be a way to frame that problem as such a optimal channel problem. Okay, and then final remarks I have is the classical optimal transport has become a very, very big field, has a wide range of applications from machine learning to statistical mechanics, and it seems many other things. And quantum versions of optimal transport does seem to show signs of similar promise, but it's in very, very early stages of development. But from the little bit that I've seen, there's not a lot yet to be seen. It does seem to be quite promising. And some references I mentioned in that same paper again. This is the paper that this talk essentially sketches background for. A more mathematical paper is one that focuses on the so-called Wasserstein metrics. It's a way to use optimal transport to get a distance between states. The second paper in turn builds on a third paper where, among other things, we discuss, this Snyman was a PhD student of mine at the time. We discuss among other things, the duality between states and channels. And this is what's used in paper 2, and the special case of which is then used in paper 1. I use the result from paper 2 and paper 1 in this last problem that I mentioned to handle this type of cost mathematically. This cost leads to if there are no restrictions, it leads to a unique minimal cost channel which corresponds to a maximally entangled state. And there's a result in the second paper here that delivers that. And then I mentioned a few papers by other people. So De Palma and Trevisan had this paper on quantum optimal transport with quantum channels. So they use a fairly similar setup than what I used here. And then the same author, along with a few others, including Lloyd, whose name you should know, they wrote at least 2 papers related to machine learning, and this is the second of them. And this quantum Earth movers distance is just one of these Wasserstein distances. I want to see, can you do machine learning using these distances? And then lastly, I just mentioned that book again, The Topics in Optimal Transport, which gives a mathematical introduction to the classical case, which is quite useful, I think, even if one wants to focus on the quantum case. Okay, thanks. That's my whole talk.
Yeah, thank you very much, Rocco. It was a fantastic, clear and interesting talk. Thank you so much.
Okay, thanks.
And I think during your talk, we gained a few participants.
Okay, that's
good. Probably a sign that that is an interesting talk. I don't know. I would like to open it up for questions. I see some of the participants already clapped virtually, but we didn't hear it. We could only see it. I don't know if there are people that have questions for Rocco. Okay, maybe while people think, you know, I was thinking during your whole talk about the connections between the optimal quantum transport, if you want, and machine learning. Yeah, has anything been done in except of the 2 papers that you mentioned by De Palma and others? To connect this strategy to some kind of quantum machine learning approaches?
Aside from these 2 papers, I'm not aware of any other. So my background in machine learning is virtually 0. I know in a classical case, it seems to have become a big field. In fact, Villani was very surprised. He mentioned somewhere that he was extremely surprised to see huge numbers of people citing his work related to machine learning in a classical case. In the quantum case, I don't think there's a lot. I think if I recall correctly, these are the only two papers. This number 5, as well as a preceding paper, which I don't list here. As far as I recall, that's the only two I've seen that connects the two, but it could be that I've missed a few recent ones.
No.
So that's this is why I say it seems to be very much at the beginning.
Yeah, no, because that's a very interesting link. Yeah, and we've been interested in quantum approaches to machine learning for some while. So we will we will look into that. Yeah.
Yeah, the argument I have is that the distances, these Wasserstein distances that you obtain from optimal transport, they claim, I haven't checked this carefully, but they claim this is very natural in a machine learning context. Similar to what happens apparently in the classical case. It seems that it's a natural way to determine the difference between some initial distribution and a final distribution. The snag, in a sense, is that they tend to be difficult to calculate. These distances are, since they are derived from couplings, they're difficult to calculate. Couplings are quite complicated in a sense. To find all couplings of two given states is not a trivial problem, not even classically, and quantum mechanically it's even more difficult. But nevertheless, they feel that it's a very natural way of doing it, and it seems there are methods to handle the problem of the difficulty of how to calculate it or how to handle this distance. But not many papers so far, as far as I know.
No, very nice, very interesting. Thank you so much. Thank you. So, are there other questions for Rocco? Please don't be shy.
Yes.
Come in, please.
Yes. No. Yeah. One first question would be: Do you have any example of so classically you already gave some example of transportation of goods from warehouse to shops, but do you know other example of application either classically or either in for quantum Bayesian?
Did you say application to what?
Application of all this framework.
Well, the applications I have not studied in much detail. This is why I mentioned this one point at the end, which I think could be a potential application. Okay. And then the other applications that I'm aware of are in quantum. This is very early, but it's in quantum machine learning. And then some people have actually attempted to apply this to statistical mechanics, though I'm not sure exactly how they've done that. So I've not studied that.
Okay.
But those are the quantum machine learning and statistical mechanics are the two that I'm aware of people attempting to apply it. But much of it seems to be in a very early stage. For example, in the statistical mechanics literature where this is used, they would, for example, use Wasserstein metrics, as I mentioned here. But those metrics are in fact not metrics. They're not at that stage when they did this initially. They couldn't yet get proper distance functions. They couldn't even satisfy the triangle inequality. So even those applications seem to be probably not optimal yet, in the sense that they didn't yet have and still probably don't have complete tools. So I think it's very early. But those are the basic applications that I've seen: statistical mechanics and machine learning.
Okay, yes, sorry.
No, I just wanted to add. So I was wondering if the problem I mentioned at the end could have applications in quantum information or quantum information processing. So I believe that this field should have applications in quantum information as well.
Yeah. No. So that's what I was thinking. Because I don't have any idea yet, but the framework looks quite versatile. So I'm imagining you can model several type of very different problems with these tools.
I think so. What I'm looking at is a very special. In fact, one can certainly generalize it in different ways, and people have looked at different versions of quantum optimal transport. They seem to vary quite a bit from case to case. So I think my impression so far is that it has a lot of promise.
Okay, and something I didn't really, I don't know, maybe you mentioned or I didn't get it, is so I imagine the solution of the optimal transport depends strongly on the cost, which on the form of the cost. And so is it always possible to solve the optimal, to find the optimal solution for any kind of cost, or
yeah, so in the classical case, there are general theorems. This is in fact what I mentioned earlier, that even in a classical case, the progress on the problem was very slow. But I mean, the problem is, I think, maybe 200 years old, but it's only in the last few decades that people in the classical case came up with methods to show that there always is a solution. Not necessarily unique. You need to make certain assumptions to make it unique. And in the quantum case, there is by now some results that tell you that there is always a solution, and in certain conditions it is unique. But even there, I doubt if in a quantum case we have a complete theory. There's not as far as I can see. But there are some results that guarantee an optimal solution. And in fact, part of these Wasserstein metrics that I mentioned is in proving that you have a metric, you actually show that the distance is attained. So there is some transport plan which attains the distance, and that is then a solution to the optimal transport problem. So it's not just that you can get closer and closer to that optimal transport, you can actually attain it. So that's part of the theory behind the metrics, is that you show that optimal transport can be attained. Even if that wasn't possible, I think you could get transport plans that get closer and closer to that optimal cost. But it turns out that there are theorems that show that the optimal transport is attained. There is some optimal transport plan, though not necessarily unique.
Mm-hmm.
Okay. And maybe one last question. Comment. So you mentioned, is that some people are starting to use this framework and tools for statistical mechanics. Do you know if they, so in such context, I would imagine like the cost function would be either the entropy or entropy prediction. Do you know
I've not looked at that carefully yet, how exactly they use it. So I'm not sure what the costs would be. Part of the problem is that there are different approaches. So the approach that I used here is, in a sense, the traditional approach using couplings. In the case of the statistical mechanics setup, they often seem to use a more dynamical approach. They set up transport plans as dynamics, and the cost isn't always so clear to me in what they do. It's slightly vague to me exactly what the cost is. They typically want something similar to what I had here, some sort of squared distance, some analogy of a squared distance, because that turns out to be the simplest case. So they seem to want to get something similar to that, but that's certainly not the only case, but that's the only case that I've looked at in some depth. So I think one would have to check the papers in the statistical mechanics literature more carefully to see what exactly they use as the cost. I've not studied that in any detail.
Okay, thank you.
Yeah, thank you, Camille. Thank you. Are there more questions for Rocco? Rocco, it doesn't seem to be the case for now, but we know how to reach you. So if there are more questions that pop up, we will get in touch. So thank you very much, Rocco. It was really a great seminar that I think everybody enjoyed a lot. And you gave us really some food for thought, because we will definitely look into the connection.
And you're welcome. If someone has a question, that we're welcome to email me.
Yes, yes, yes. And I'm sure Camille will look at the connection to statistical mechanics because that's something close to his heart. Yeah. So
that's something I want to look at in a bit more detail as well, but I simply haven't had time to do it yet. So I've only looked at it very
but you know, since we are all based in South Africa, it shouldn't be too difficult to start some collaborations. Yeah, that would be really very nice. Yeah.
Yes.
And we are really looking forward to that. Yeah.
Okay,
so
thanks
Rocco,
very much.
just one last question, Rocco,
Yeah.
that I didn't ask you previously. Are you happy that we put the recording of this lecture in our NITheCS YouTube channel?
Yeah, I think that's fine. Yeah, I have no problem with
perfect,
that. Yes.
Perfect. Then we will do it after the talk.
Yeah.
Perfect.
Okay.
And we will share the link with you so you can advertise your paper.
Okay. Thanks a lot.
And congratulations to the paper because it's really very interesting. I thoroughly enjoyed it. Thank you very much.
Okay. Thanks very much.
Thank you, and all the best to your dog.
Yes, I hope he recovers.
Quickly.
He's here next to me, sleeping.
Okay, very good.
Okay.
Excellent.
Bye-bye.
Thank you very much. All the best, and thank you to all of you for joining us today. Thank you. Thank you very much.
Bye-bye.
Bye, Rob.
Okay, bye. Bye.
Bye-bye.